Okay, everyone, so in this video, let's take a look at a set of objects V, which is going to be all of R3. And we're going to use the usual vector addition with vectors in R3, but we are going to define scalar multiplication a little bit differently, in that we're going to take C times U to be actually apply minus C. We're going to multiply each component of U by minus C. Okay, so C times U would give us minus C U1, minus C U2, minus C U3. And so if we were to look at the various axioms for this set of objects in these operations, since we have not changed addition, we've already verified that if we've got R3 with the usual addition, then vector addition satisfies all of these properties. I'm missing one parenthesis over here. So all of these properties follow from what we know about usual vector addition with vectors in R3. And let's think about what happens with this newly defined multiplication, where instead of multiplying by C, we're multiplying by minus C. So still, when I take C and multiply it by any vector U in R3, we will get a vector in R3. So this set is closed under this scalar multiplication. That is fine. We can check that this distributive property, which says if I take C times the usual sum of two vectors, then I would get minus C times the sum, minus C times the sum of the second components, minus C times the sum of the third components. That is equal to what I would get if I took C times U and then added C times V, because we distribute that negative sign in for both of those operations. So far it seems like all of these properties are working. If I take a look at the other distributive property, namely if I take C plus D times U, then I would multiply by each component of U by minus C plus D. And if we compare that to taking CU plus DU, that would be minus CU1 minus DU1, and so on. So these two distributive properties work just fine, even with this kind of weird scalar multiplication. And let's take a look at the associative property for scalar multiplication. And this one does not work. So for example, if I take C and D to be 2 and 3 respectively, then if I take C times D times U, so if I first multiply 3 times U, I would get minus 3U1, minus 3U2, minus 3U3. And then if I multiply that by the scalar 2 again, we then multiply each of these by not 2, but minus 2. So we get 6U1, 6U2, 6U3. But if we compare that to what happens if we first multiply 2 times 3, I would get 6. And then I multiply that scalar 6 times U, I would get minus 6U1, minus 6U2, minus 6U3. So at this point, property 9 is not satisfied. Wow, we made it so close, made it through 8 axioms. Axiom 9 fails, so therefore this is not a vector space. And if you're curious about thinking about the multiplicative identity, we actually do have a multiplicative identity in this case. Namely, if we set C is equal to minus 1, then minus 1 times U, as we defined it in this way of multiplying, would give us the same vector back. So we do have a multiplicative identity, which happens to be minus 1. So we have 9 out of 10 properties that worked, but that is not good enough. Property 9 did not work, so this is not a vector space.